whenever you're designing anything, whether it be a car, a data acquisition system, a blender, literally anything, you have to consider your design constraints alongside what you actually need. In case of a data acquisition device, you need something that records data quickly, reliably, and in some cases compactly. We'll get to that later. That means you have to balance cost, performance, size, weight, reliability, ease of use, so on and so forth, on and on and on. This video is going to go over how you should go about balancing those and give you some initial thoughts about what different methods you might want to pursue. This is going to start out getting into some more advanced stuff, but here what we try to do is we have separate ADCs that communicate to our teensy, which is a microcontroller, over I2C, a data transmission interface that allows us to read analog values from things like brake pressure sensors, linear displacement sensors, if we need strain gauges, any of that type of stuff. And then we use just digital reads for Hall effects, which a Hall effect sensor helps us get like RPMs. So the way that we've decided to build our at least initial at this phase, this is recorded on 11/3/2025, so we may change this in the future, is we have a singular microcontroller mounted to the back of the car. This keeps costs down because microcontroller is only about $30. This microcontroller records data to an SD card over binary. This helps us with performance, as we're able to get somewhere in the neighborhood of 220,000 writes of data per second. Now, obviously, that's going to be dependent on actual data packet size, but we're able to get plenty. Our highest polling rate right now is about 1600 hertz. Our teensy saves to an SD card, which gives us unparalleled performance. According to my calculations, it's about 5 to 6 times more compact than a JSON packet, which means about 5 to 6 times more theoretical data you can write, alongside being even more performant because we don't have to do as much string concatenation and things like that. For those of you who don't know, string concatenation is basically where you take a bunch of strings and smash them together. It's an expensive operation and something you want to avoid when possible, especially on a microcontroller. But all of this to say is that there's a lot of things happening at the same time. You want to pull your sensors as fast as possible, you want to get the data as soon as it's available, and you want accurate timestamps on the data so you know when it actually happened. So, with all that said, let's get into the general overview. Let's put that stuff aside. We'll have later videos going into all the details. Let's talk about what the main things you actually care about are. Key idea number 1, cost. You can have designed the best data acquisition system in the world, but if it costs, and this is an actual example, $300 to get these new boards in that will allow you to work with them, it's going to be really difficult to convince people on your team that you should throw that type of money around, because you don't know if your first boards will work. You don't know if your system is going to instantly break. Everything is unknown, especially in the world of off-road. So what you have to do is start small. You want to go step by step. First step, find what microcontroller you want to use. I would recommend starting with a Teensy 4.1, as they have a built-in SD card. They are able to write and read plenty fast, as I was going into earlier, and they are incredibly easy to program due to Arduino. There are tons of libraries available for them, and they have built-in ADCs as long as you're working with 3.3 volts. Cool. Now that we have that aside, let's go ahead and get into performance. There's no point having a data acquisition system if it can't get you enough data. There's something called aliasing in signaling, which is basically when you are pulling too low to actually see what's happening. For a digital signal, or at least for an analog signal, I believe it's the same for digital, calculation might be slightly different, you want to be able to pull at double whatever the rate of the signal actually is, plus 1. And the reason for this is, let's say you have a sine wave, like what's showing on the screen. You can see that when we pull at intervals of pi halves, you can perfectly reconstruct sine of x. Awesome, but if we put sine of 2x in, all of a sudden it looks like it's always 0. This is exactly what can happen if you don't pull high enough, and does mean that you need at least a minimum performance level. Performance is going to be dictated from everything from your microcontroller to your SD card, like how fast that can handle speeds. If that ends up being a limiting factor, I doubt that'll be the case, but it's possible. And your ADC polling rate. We've used ADS1115s in the past. We're switching to ADS1256s because ADS1115s have a maximum polling rate of about 860 hertz at 15 bits for the entire device, at least in single channel mode. You can get a little bit better in differential. But for an ADS1256, you can do 33.3 thousand samples per second. Now that's not per channel because, that's not how they market such things, but that's overall, and that's a clear performance increase. You need more speed. So for now, don't worry about those model numbers and things. Just know speed is good to a point. If it's too expensive, you're back to the cost problem. Doesn't make sense. Now, reliability. This is the biggest one of all. I've been doing this for a while now, and I've built so many systems that in the lab work perfectly. And as soon as they start moving, everything breaks. An exact instance, last Sunday, literally yesterday, we were out testing. Our brake pressure sensors looked great when we were standing still. You'd pump the brake, everything reads perfectly, and then you start driving the car and all of a sudden it cuts out. I'm guessing right now it's an electrical connection that's getting exposed due to, or a loose electrical connection that we were seeing when the car starts vibrating. Because if your connector is a little bit in there, an analog signal is very resistance dependent. You have to make sure your resistance is just about constant, otherwise there's a problem. When you start vibrating, if your connectors start kind of doing that, your resistance is going to change. It could even just come completely disconnected. So you gotta build a reliable system. If it breaks before you can save the data file, you have nothing. If it breaks before you finish with your tests, you've driven all the way out to wherever you're testing, and then you've kind of let everyone down. It'll take a while to get to the point where you can be reliable, but some things you want to consider are waterproofness. Look for things that are IP68, IP69 plus rated. You want waterproof connectors. I'd recommend Deutsch plastic DTM connectors off of Amazon. They're like $20 for a set of I think 4 for both. If you think about it, you have 4 wheels on a car. That means at most you probably want 3 RPMs because usually the rear wheels are tied together. So different for front right, front left, and then back. And then you might want an engine RPM as well so that you can see your CVT ratio. That's 4. $20 for all your RPMs. Add in some analogs. Let's say you want to do LDSs. One of those per shock, that's another 4. $40. The cost adds up, but it's worth it for those. And this is a place where even though cost is a key consideration, you want to instead go with spending more money. More money does actually mean more better in most cases when it comes to connectors. We'll have more videos going into how to properly crimp those. Please watch those before trying to do it. It is incredibly important that you properly do it, otherwise things will not go well. Next, we've covered cost, performance, reliability, size, and weight. The goal of off-road and Baja is to win. I mean, also to learn, but we like winning. If you have a big, heavy box hanging off the back of your car, it's going to be slower. There's no way around it. Let's say you have 20 pounds of data analysis equipment. It's the best data analysis system in the world. Well, our car weighs 440 pounds. All of a sudden it's 460 pounds, which translates to I don't know, that's probably a 20th the weight added. That could legitimately change the way that the car performs. Sure, you'll still get pretty good data, but it will affect the performance characteristics of the vehicle. There's no way you want to run that during competition. So you have to decide what sensors you want to run during a testing day, what sensors you want to run during a competition. How can you prioritize the weight between those? I would recommend having separate testing setups. The one for a testing day that you go much bulkier, much more built out, has a lot more features, and then competition, which basically tells you if the car is alive, because you can be the best computer engineer in the world. I'm sorry, but the mechanical people are not letting you fix your data acquisition system while they're racing. They want to do laps. It's just how it goes. But so far, that's cost, performance, reliability, and size/weight. Those are the 4 main things you have to deal with. But there's one more thing, and it's really big for collegiate competitions: complexity. When I first joined off-road, I had no idea what I was doing. I got almost nothing done, even though I worked a ton, and I just couldn't understand anything. And the entirety of what the old team had was completely lost because I couldn't understand. I was the last one left. I rebuilt the entire thing from the ground up, and that's just taught me a lot, but it also delayed the time we could get data for a long time. It's very important to have your code be accessible. I'm not saying don't do crazy optimized stuff. I'm actually working on something right now that uses GPUs to accelerate binary conversion to JSON with CUDA and a bunch of processing and parallel stuff and pointer things and all sorts of things that are way too complicated for a freshman to understand. Unless they're absolutely cracked, then maybe. But anyway, what you need to do is make sure that your stuff is accessible. Have parts that are written in Python. If you don't need to use C++, don't use it. If you're writing, working on your Arduino, sure, you need to use C++ for that. It would be ridiculous to use any other language than a low-level one. But if you can write in C++ instead of assembly, probably use C++. And make sure that your code is written so that it's easily readable. I'm going to put some pictures up here of what we have. You see how there's all these functions that are init debug LEDs or activate ADCs. It's very important to make it that a new member can look at your code and generally understand what's going on. They don't have to understand all the fancy pointer math. They don't have to understand all the fancy register work. They'll learn that as they go, but they need to know the basics so that they can both understand what's happening, be engaged, and have the chance to learn. The point of College Baja is winning, but also learning having fun spreading it on. If you want to build more than just a good team, if you want to build a legacy, you have to make sure that you communicate it. So watch that complexity, do the cool fun things, make it difficult, but make sure that it's well documented when you do that, and make sure that it's distilled down to something easier to understand. So I hope you've enjoyed this video. It's actually the first one we've put out on the channel, so it's probably a little rough around the edges, but please leave feedback on how you'd like us to adapt or stay with or change the formula. And yeah, thank you for your time.